This is a Martian observation fleet, and it will orbit the red planet for the next 50 years, watching every storm, every dust devil, every faint seismic rumble. Humans were born on Earth, but they were never meant to only look up at the stars. In which direction will the satellites orbit? And how will they relay data back to Earth? Will the number of satellites grow in the sky above Mars over the next 50 years? What happens to the thin Martian atmosphere as the sun's cycles change? And what will the time delay be once human colonies arrive on the surface? And what happens during the last 10 years of orbital observation to prepare humans for the conditions below, such as lower gravity and red skies? But why are these satellites here, around Mars? Because it is the closest planet for human expansion, at only 12 light minutes away. With high-resolution sensors, the Martian observation fleet will scan every canyon, every volcano. There are 50 satellites in orbit now, and the mission starts now. The first satellite enters Martian orbit, firing up its ion thrusters. It takes 3 months from Earth launch to arrive and enters stable orbit. Then begins the global mapping phase. The fleet passes over Olympus Mons and Valles Marineris, using radar and infrared instruments. It took 8 minutes for signals to reach the Moon, 12 minutes to reach Mars. They orbit in a polar path, so the entire surface is scanned. Earth and Mars rotate at different speeds. The orbital fleet ensures continuous monitoring. Data streams back to Earth with a delay. 12 minutes for signals, 24 minutes round trip. The orbit is maintained using minimal thruster burns. The satellites are equipped with solar arrays and nuclear batteries to function during dust storms and darkness. Now begins the deep scan maneuver. Synthetic aperture radar instruments fire up. The satellites align to scan under the Martian surface, looking for ice caves and lava tubes. They circle Mars every 2 hours, scanning repeatedly due to orbital momentum. In space, the satellites continue scanning, pass after pass, for decades. The mission control on Earth now brings online advanced AI analysis systems to process the vast data, from terrain maps and subsurface scans to atmospheric readings, dust storm tracking, and seismic activity monitoring. There are also atmospheric sensors on board, measuring methane spikes and seasonal changes. Inside the control modules, the satellites adjust their instrument orientations to optimize coverage. When solar power is low, the satellites adjust to nuclear power. The orbiting fleet sends data streams to deep space network dishes on Earth during favorable alignment windows. The satellites coordinate with each other using laser links, creating a mesh network to avoid data loss. 4 days after full deployment, the fleet begins to detect magnetic anomalies and subglacial ice deposits using their sensors. The Martian orbit is not crowded like movies suggest, but each satellite has collision avoidance protocols. The fleet is designed with shielding against micrometeorites. The satellites use tracking sensors to dodge debris and clear their orbital paths. The Martian sky is filled with dust clouds and thin winds. The satellites have been circling Mars for 1 month after arrival, passing over familiar landmarks, the polar ice caps, the equatorial canyons, and volcanic plains. The orbiting fleet keeps track of the seasonal dust storms. When the satellites arrived, there were 50 operational units. This number will grow with new launches. Over the 50-year mission, onboard software upgrades will evolve the AI systems managing the data flow. The onboard engineers monitor the solar cycles on Mars to understand the effects on the thin atmosphere and dust levels. The satellites monitor changes that could impact future human landings. The first major dust storm during the mission marks a test for the satellite's durability. The storm darkens the skies for weeks, reducing solar power. Each satellite's systems switch to low power mode. Data transmission slows, but continues using nuclear backup. The orbiting fleet is now 12 light minutes from Earth, with a communications delay of 12 minutes each way, and time dilation effects are negligible, but critical for operations. Mission Control calculates precise windows for data downlink and command uplink during optimal alignment with Mars. As the decades pass, the orbiting fleet detects weak radio signals from the Martian surface, unexplained and repeating. The first signal is a simple pulse, detected during a quiet window. More signals follow, creating mystery and urgency on Earth. Discussions about possible underground geological phenomena or unknown natural signals. The orbiting fleet adjusts scanning protocols, focusing on the southern hemisphere, where signals are strongest. Sensors scan deeper under the surface, searching for caves, lava tubes, and ice deposits. The analysis teams on Earth debate the origin of these signals. Data keeps streaming from the orbiting fleet to Mission Control. The satellites continue to watch Mars as plans for human colonization develop. The orbiting fleet will remain for the next 50 years as silent guardians above the red planet, preparing for the day humans will finally descend to the surface and begin a new chapter on Mars. A new kind of constellation surrounds Mars now, not the constellations made by distant stars, but a net of steel and composite, a living skin of human technology. 37 satellites form the Great Orbital Net, an array launched over 2 decades, piece by piece, by agencies, coalitions, and even private mining interests. Each satellite is a silent eye, peering down on the swirling dust devils, the shifting dunes, and the thin, frosty layers that glitter in the dawn light. They track the chaotic weather patterns that form as Mars's carbon dioxide snows melt under sunlight, creating pressure waves that sweep across the plains. They map magnetism in detail never seen before, tracing remnants of the planet's ancient, lost magnetic field, buried in pockets of crust. They record the faint, eerie pulses of radiation storms when solar winds crash into Mars's unshielded sky, reminding everyone of the need for underground shelters if a human colony is ever to survive. The Great Orbital Net also becomes the backbone of Martian communication. Each probe bounces data between landers, rovers, and orbital labs, creating a web of constant monitoring, a living archive of the planet's changing face. In the quiet data streams, something changes. One satellite, part of the deep penetrating radar cluster, picks up unusual reflections beneath the crust near Elysium Planitia. At first, the readings are dismissed as noise reflections bouncing oddly off rocky layers. But then, a pattern emerges. Heat signatures, void pockets, subsurface echoes that dance just above the noise floor. Follow-up scans reveal networks of tunnels or caves, perhaps formed by ancient volcanic activity. Yet some of the geometry is suspiciously regular straight edges where none should exist, angular corners beneath miles of rock. Questions multiply across mission control centers on Earth. Are these natural lava tubes, waiting to shelter future explorers from cosmic radiation, or something older, crafted by a force that left no other trace? Small landers are dispatched to scan the entrances of these voids. They drop seismic charges, measuring the vibrations echoing back. Every reading suggests the same story. These spaces are vast, layered, and in some regions, warmer than they should be. The possibility of ancient water reservoirs, locked in ice or brine, keeps the science teams awake at night. But others begin to whisper, could these be the remnants of something artificial? Structures abandoned beneath the regolith, silent and dark, waiting for the thin sunlight of Mars's day to wake them. Elsewhere above the rust-red horizon, a different kind of machine hums to life. The first nuclear thermal propulsion craft is ready for its test flight, a deep space vessel designed to break the barriers of time. The ship is a spearhead of the new interplanetary fleet. It carries a reactor no larger than a compact car, but powerful enough to heat hydrogen to thousands of degrees, expelling it with such velocity that the craft can cut interplanetary travel times in half. It is not a sleek craft. It is functional, armored against radiation, covered in gold foil and thermal tiles that shimmer as it rotates in orbit. The ship begins its burn. A low, guttural hum turns into a high-pitched resonance, vibrating its structure. Bright hydrogen exhaust plumes flare invisible except for the flickering distortions in the thin light. The engine runs flawlessly, executing its high-speed test run from Earth transfer orbit to Mars orbit in record time, cutting months from the journey, rewriting the logistics of deep space travel. Mission Control holds its breath as the craft decelerates, slipping into a high Martian orbit. Engineers around the world celebrate quietly. The barriers to Mars are falling, one burn at a time. This is the ignition of a future where the solar system's distances are no longer vast oceans but navigable lanes, waiting for ships to cross. During a routine scan of the polar ice caps, a low-frequency pulse is detected. At first, it is thought to be an echo from the lander's radar ping, but the pattern repeats. It is too structured to be geological, too precise to be natural seismic noise. The pulse is narrow-band pulsing once every 8 seconds for 23 minutes. Then it falls silent. Teams scramble to confirm the reading, rerouting satellites to monitor the ice cap. Instruments tuned for subsurface sounding now listen for whispers in the Martian crust. Speculations spread like wildfire. Is it geological activity? Perhaps ice cracking under stress? Is it an instrument malfunction? Or could it be something else, something older, waking under the pressure of shifting ice? The pulse remains unexplained, but it changes how Mars is viewed. It is no longer a silent, dead world. It is a world that might still speak in pulses and echoes, waiting for humanity to listen carefully enough to hear its secrets. While the satellites sweep overhead, a cluster of human habitats expands on the surface. Small research domes at Gale Crater and Valles Marineris gather dust in the morning winds. Solar panels unfold like flowers, tracking the weak sun across the salmon sky. Inside these domes, scientists monitor air pressure carefully, living under layers of Kevlar and composite shielding. Hydroponic systems hum quietly, nurturing kale, lettuce, and potatoes under LED arrays. Water reclamation units hiss as they recycle every molecule of vapor. Green is precious here. The sight of a single leaf becomes a reminder of Earth. On the walls, screens display the latest orbital maps, weather patterns, and the slow creep of dust storms across the plains. Every day begins with an EVA, an expedition into the Martian day, checking instruments, collecting soil samples, and watching the horizon for the rising towers of dust that can swallow an outpost in hours. Life here is measured in oxygen levels, battery percentages, and water reserves. But it is also measured in the quiet moments when the sky turns purple and Phobos crosses overhead like a pale ghost, reminding the settlers that they are not alone in the dark. Year 2025 was the year humanity placed its first plant experiments under open Martian sunlight, shielded in carbon dioxide domes. By year 2050, these experiments have evolved into small-scale terraforming test sites. At select locations near the equator, black dust is spread over ice patches to increase heat absorption. Carbon dioxide from the polar caps is released, creating thin plumes of vapor that rise into the air, trying to add whispers of warmth to the thin Martian atmosphere. Microbial colonies, engineered to withstand radiation and low pressure, are deployed on rocks, forming dark films that slowly metabolize minerals, producing tiny amounts of oxygen. Each colony is a laboratory, an experiment in building a breathable world, molecule by molecule. Satellites of the Great Orbital Net monitor these experiments, tracking atmospheric changes measured in parts per billion, watching for the day when Mars's skies may thicken, if only slightly. Mining platforms in Mars orbit begin extracting resources from Phobos and Deimos. These small, irregular moons provide raw materials, water, ice, metals, and regolith processed in orbit to build fuel depots and structural panels. 3D printers in orbit churn out components for habitats, satellites, and orbital mirrors, expanding the industrial footprint around Mars. The goal is simple: reduce dependence on Earth, create a closed-loop economy in orbit, and make Mars a stepping stone rather than a drain on Earth's resources. As the nuclear thermal propulsion craft returns to Earth orbit for inspection, its engines cool. The data it has gathered rewrites propulsion models. Plans are made for a manned mission using this new technology, reducing the travel time to Mars to under 3 months, making crew rotations possible, and enabling rapid medical evacuations if necessary. The cultural shift. Mars changes the people who study it. Students on Earth now train on virtual Mars missions, experiencing the slow EVA crawls, the hiss of the airlock, the radio crackle under the delay. Children learn the geography of Mars as easily as they learn the continents of Earth. Artists create music inspired by the winds of Mars, using data from atmospheric sensors to generate haunting melodies. Writers pen stories of families who will one day live beneath the surface, their windows looking out onto red dunes, their nights spent under skies so clear they can see the Milky Way in sharp relief. The low-band pulse from under the ice cap becomes a story told around the dinner tables of Earth and Mars alike, a reminder that the universe still holds mysteries, and that every mission is not just about technology, but about discovery. Mars, in year 2050, is not yet a world with cities and oceans, but it is no longer just a cold, distant rock. It is mapped, monitored, and measured, but it also holds mysteries that evade the reach of even the most advanced sensors. In orbit, the great orbital net glows in the reflected sunlight, each satellite a sentry and a storyteller relaying the whispers of the planet below to a species hungry for knowledge. Beneath the surface, heat signatures wait in darkness, and the low-band pulse once heard is never forgotten. Humanity's ships, now powered by the heat of splitting atoms, reach Mars faster, their trails marking the beginning of routine interplanetary travel. And as Mars listens back, humanity leans closer, its ears tuned to the silence, its eyes watching the thin skies for dust devils and dawn light, waiting for the day when boots will walk across its plains, not for days, but for lifetimes. This is the year humanity turned Mars into its mirror, orbiting it with eyes that never close. No landing, no boots in red dust, no flags, no footprints. Only watchers in the cold dark, spinning around a silent world, recording every whisper of wind, every swirl of dust, every flicker of sunlight on rock. Sending satellites and missions around Mars to monitor everything became the plan, not to conquer Mars, but to know it. To watch it from above with the patience of centuries, capturing data humanity could never gather before. Mars, a world humanity could see with telescopes for 400 years, now turned into a living map, updated in real time. The multi-agency satellite deployment begins quietly. There is no single hero. Instead, it is a network of engineers in Tokyo, Houston, Delhi, Paris, and Nairobi, aligning new probes to slingshot around Earth before being thrown toward Mars on narrow windows. The goal is constant Martian surveillance, without risking crewed landings. No human deaths, no stuck rovers, only observation. Eyes in the void is what the media call the project, but on the ground, they call it the Continuous Mars Monitoring Array. It starts with the launch of 8 new satellites, each equipped with hyperspectral imagers, magnetometers, and climate radars, forming a grid around Mars. Each satellite orbits on a carefully calculated path to maximize coverage while avoiding collisions. At sunrise over the Pacific, rockets roar as these satellites depart, their ion engines humming softly as they adjust their orbits during the months-long journey. From Earth, they vanish into blackness, tiny dots racing away from the gravity that once held them down. Once they arrive, they ignite their engines again to slow down, captured by the thin gravity of Mars, each satellite shifting into its slot like beads on an invisible necklace around a cold red marble. Their solar panels unfurl like wings, their sensors open like eyes. They begin to watch. They record the frost on Olympus Mons at dawn, the shifting carbon dioxide snow near the poles, the pulsing winds of dust storms that can cover continents, and the glow of auroras flickering over the thin air. For the first time, A constant stream of data flows back to Earth, terabytes of images, atmospheric readings, magnetic fluctuations, temperature maps, and dust storm trajectories. The data uncovers new storm systems, showing how dust devils grow from small eddies into towering pillars that crawl across the plains for days. It finds ancient water traces hidden beneath sand, channels that may have flowed only a few million years ago, now exposed by subtle shifts in temperature and moisture patterns recorded by the satellite sensors. Back on Earth, supercomputers stitch this data into simulations so real that virtual reality explorers can walk on Mars without leaving Earth. Students in Rio, engineers in Lagos, children in Manila can wander through Martian canyons, watching storm clouds drift in real time. Humanity starts to learn Mars as it truly is, not as an idea, but as a living, breathing world. The year passes, and the watching a silent world phase begins. Orbiters stream even more data, expanding the monitoring grid to 16 satellites. International agencies share the live feeds. Farmers in Argentina check Martian weather as casually as checking Earth's forecast. Scientists discover a system of ancient floodplains, showing evidence of water flows bigger than any Earth river, locked in red stone. Mars becomes familiar, but Earth's ambition does not stop there. A breakthrough mission launches, testing a technology long theorized, long feared, and finally built: nuclear thermal propulsion. For decades, chemical rockets were kings, but they are slow. Nuclear engines promise faster journeys, reducing the time from Earth to Mars from 6 months to 90 days. The launch is quiet, no live feed, only a press release afterward. Successful ignition of the NTX-1 nuclear thermal propulsion test vehicle. It is a cylinder of reinforced alloys and carbon composites, carrying a small scientific payload and a propulsion system that heats hydrogen using a nuclear reactor, ejecting it at high speed to generate thrust far beyond what chemical rockets can offer. As it fires, the NTX-1 glows faintly, a ghostly blue flame visible in deep space. It accelerates faster than any Mars mission in history, building speed in a continuous burn before shutting down to coast at record velocity toward Mars. 90 days later, it arrives in Martian orbit, stunning the global scientific community. The probe sends back high-resolution images of Valles Marineris, the Great Canyon of Mars, in colors never seen before. The engine, having proven itself, becomes the benchmark for future missions. A new path is opened, the potential for human travel to Mars in months instead of years. And yet, there is caution. The mission is robotic, the probe is uncrewed, the risks carefully calculated. Humanity's exploration of Mars remains a dance from a distance, watching, learning, and preparing for the day when the leap will finally be made. It is the fourth mission using nuclear propulsion. The probe, named Aethon, is designed to orbit Mars for 2 years, studying the planet's magnetosphere and interior with a suite of advanced instruments. It is equipped with ground-penetrating radar, seismometers that can measure quakes from orbit, and a magnetometer sensitive enough to detect slight shifts beneath the crust. For months, Aethon sends back stunning data. It detects magnetic anomalies near the Tharsis region and a rapid magnetic shift beneath Olympus Mons, Mars' tallest volcano. The data suggests a plume of molten rock moving deep below the crust, a sign that Mars may not be geologically dead after all. Fensolence. The signal from Aethon stops abruptly during a routine orbit adjustment. Tracking stations around Earth wait for the next pass, but the probe does not respond. There is no final transmission, no signal of failure, only the quiet emptiness of space where Aethon once was. Some speculate a micrometeoroid impact. Others, a systems failure triggered by the intense magnetic fluctuations it was studying. A few wonder if the probe detected something unexpected, something it was not prepared to handle. In the mission control rooms, engineers replay the last few minutes of telemetry, looking for clues, but find only data that ends mid-transmission. The probe that never returned becomes part of Mars's story, joining the scattered wreckage of past missions' silent observers, now lost to the void, drifting forever around the red planet. But the monitoring does not stop. New satellites are already being prepared, built in modular labs in orbit around Earth, and launched from reusable heavy-lift boosters that leave and return in days. Nuclear propulsion becomes more refined, with prototypes tested near the Moon before being sent to Mars. The monitoring network grows orbiters, tracking storms, temperature changes, magnetic pulses, and seasonal frost with ever greater precision. And on Earth, the Martian monitoring grid becomes as routine as Earth weather satellites, integrated into global networks, part of climate models, and studied by every space agency and university. The orbiting metropolis around Mars is not made of cities, but of eyes and sensors drifting in precise formation, circling the planet endlessly. Mars becomes the most observed object in the solar system after Earth, its secrets gradually unfolding under constant watch. In the labs and control rooms, the data from Mars sparks debates. Could a crewed mission follow the paths charted by these eyes in the void? Could nuclear propulsion cut travel time enough to send humans safely with minimal radiation exposure and reduced life support strain? Scientists develop concepts for autonomous fuel depots around Mars, refueling future missions with hydrogen mined from the Martian moons, Phobos and Deimos. Robotic miners and fuel processors are tested in simulation, designed to be delivered by the same nuclear propulsion systems that proved themselves in year 2052. Meanwhile on Mars, the orbiters detect patterns. Subtle seasonal methane spikes, temperature inversions before dust storms, faint pulses in the magnetic field near ancient lava tubes. Each discovery becomes a piece in the puzzle of Mars's past and potential future. Students around the world use live data streams in their classrooms, learning to code by analyzing Martian weather. Virtual reality explorers experience Martian dawns in real time, watching the frost recede as the thin sunlight spills across the red plains. Humanity is not on Mars yet, but it is closer than ever before. Every day, every orbit, the eyes in the void gather the knowledge that will guide the first human steps onto the planet when the time comes. In this era, Mars is not a dream. It is a monitored, measured, living world under constant observation. Silent, patient, waiting,